You're muted.
Thanks, Connie. Hi, everyone. Good morning, good afternoon, wherever you may be. Welcome to Phi Tau Sigma's fall webinar series. My name is Elizabeth Grasso-Kelly, and I'm the current president of Phi Tau Sigma and the past chair of the program committee for Phi Tau Sigma. We're pleased to offer this webinar today and the rest of our webinar series to guests on live viewing, and then to our guests or to our members on recorded viewings as well. For today's session, we will be discussing microplastics and nanoplastics, and we have two esteemed colleagues here with us today to present to us on these topics. Our moderator and host for today's session is Dr. Connie Weaver. Dr. Weaver is a distinguished professor of research at San Diego State University and the 2023-2024 chair of the Future Directions Committee for Phi Tau Sigma. She is also the organizer of today's session. So I'd like to hand it off to Connie so she can introduce our speakers and moderate today's session. Thank you.
Thank you, Liz. It's so great to have everyone join us. The Future Directions Committee initiated a series of seminars on behalf of Phi Tau Sigma last year, and one of our members was particularly passionate about micro and nano plastics, but it took us months to figure out who to invite, and we're so excited about these speakers. Now, neither of them were trained in food science, but as with all complex questions these days, it takes a interdisciplinary perspective and teams working together to solve the problems. So as we became aware in the environment that micro and nanoplastics posed a risk, then of course our food supply is going to reflect that risk. But also food scientists are starting to have innovation in this space as they understand nanotechnology so that they can create innovative ways to improve health of our food supply. So I'm real excited about our speakers today, Doctors Timothy Duncan and Scott Coffin. I'll introduce Timothy Duncan, who's going first, and then I'll introduce Scott Coffin after the session with Tim. So we'll have a few questions after each of the speakers because their topics are a little bit different, but then hopefully we'll have time at the end for a more general discussion with the speakers and the audience. So Timothy Duncan received his undergraduate degree in chemistry in 2000 from Haverford College, that's just on the outskirts of Philadelphia. He attained his PhD in physical and organic chemistry in 2006 from the University of Pennsylvania. Then he went on to do postdoctoral training at the University of Pennsylvania in single molecule fluorescence microscopy and conducting polymers. Since 2009, he has been a research scientist at the US FDA's Division of Food Processing, Science, and Technology, where he studies nanotechnology, adapted food packaging, and sensors. He is also a designated subject matter expert in nanoscience, food contact materials, and microplastics. We welcome you.
Okay, thank you. Let me bring this up, and hopefully someone can confirm for me that they're able to see.
Yes, but you will want to put it in presenter mode.
Yeah, there we go. Does that look okay?
Looks great.
Great. Well, okay, thank you so much for that introduction, and I want to thank you also for the opportunity for me and Scott to come here and share some of our perspectives on this important topic. Just a brief disclaimer, nothing I say here today should be considered to represent any official guidance or policy positions from the FDA. And I'd like to start, though, with a little bit of history. Several years ago, when this topic of microplastics first really started to gain momentum, both in among the scientific circles and also the public lexicon. FDA, as it often does with emerging issues, formed an internal working group on this topic. The idea being to kind of bring together experts from a variety of different technical areas and policy areas together into one room to review the state of the science and figure out what the major knowledge gaps are, and also to help the agency respond to inquiries from stakeholders. I don't actually do microplastics research currently. My research is in polymer packaging and nanomaterials, but since that research is kind of at the crossroads of plastics and small things, I was well positioned to become one of the technical experts, subject matter experts in this area. So that's how I got involved. One of the first things we did is once the microplastics work group was formed at FDA was to basically download as many papers as we could and meet regularly to discuss them and try to understand what the current state of the science was, and identify priority areas for research. That process took a year or two, and once we were finished with it, we had sort of accumulated this really deep knowledge base on this topic, and so a few of us decided that we wanted to turn that into a perspective, a research article, which we published earlier this year in Analytical Chemistry, and the title page of that is shown on the slide right now. So my goal today is to sort of walk you through some of the high-level points of this paper, but obviously I can't go through it in an incredible amount of detail. So the reference is there, so that if there's anything else that you want to explore in a little more detail, you can certainly consult that. So I'm going to start by giving my perspective of what the state of the science is for micro nanoplastics in human foods. I'm going to be focusing on human foods and their potential impact on human health. I'd like to step back from microplastics first for a second and talk about plastic waste in general, to kind of give you a little bit of an idea of the scope of the issue. So what you're looking at here are some data that I extracted from yearly municipal waste reports that are published by the Environmental Protection Agency, United States Environmental Protection Agency. So basically, they go through every year and basically analyze, do an analysis of what people in the United States throw out. There's a lot of granularity to the data that's presented in these reports. So what I pulled out here are just related to packaging waste in the United States that enters into municipal waste streams, broken down by the base material that waste is composed of. So plastic, glass, paper, and so forth. And it's the weight fraction that's being plotted here as a function of time. Plastics are in red, and it should be immediately apparent that over the last couple of decades, the prevalence of plastic in the waste stream for packaging has increased steadily, whereas the proportion of other materials has declined. So this is just a way of showing that plastics have become a lot more popular due to their attractive properties. And because they are more popular in consumer products in the United States, they tend to be thrown out proportionately. Just some basic numbers. 2018, Americans threw out about 4.5 million tons of plastic packaging. If you look at all plastics, that number goes up to about 36 million tons of plastic. So it's quite a bit of plastic that enters our municipal waste streams here in the United States. About 3/4 of that is landfilled, so entered directly into terrestrial environments. About 16% of that is recycled, and about 8% of it was incinerated. This does not account for plastic that enters waste streams globally. This is just in the United States. So if you consider the entire world, those numbers would go up quite a bit. This also does not include plastic that is litter intentionally thrown into the environment or accidentally enters the environment, not through municipal waste streams. When we think about plastic waste in the environment, the most common context is marine environments, and that's because a lot of the plastic waste does end up in rivers, lakes, and oceans. when plastic waste enters into those environments, they are subjected to a number of mechanical and chemical processes, such as wave action, wind, salt, solar radiation, that break down those plastics gradually over time. So those plastics get into smaller and smaller pieces, and when eventually they would get small enough that we would consider them to be microplastics. And then if they further degrade into even smaller pieces, we might consider them nanoplastics. There is no official demarcation line between what a microplastic is and a nanoplastic is. Those definitions don't really have a lot of consensus, and they vary from organization to organization. For the purposes of this talk and the paper, we considered 1 micron to be the demarcation line between nanoplastics and microplastics. So microplastics would be anything that ranges from about a micron up to 5 millimeters, and nanoplastics anything below 1 micron, or 1 micron in size, at least in one dimension. But that's not any kind of official FDA definition. The concern, of course, is that if these particles get smaller and smaller, they're more likely to be ingested or otherwise taken in by marine organisms. And marine organisms that take those in could be eaten by other marine organisms, and so on, and so that they become bioaccumulated into higher trophic levels. And eventually, they might be accumulated into an organism that is a human food source. And so this would be a route for oral exposure for humans to microplastics and nanoplastics. There's also been some concern about the potential for microplastics and nanoplastics to bind onto other pollutants in marine ecosystems, like heavy metals or organic pollutants, and be a vector for humans to also be exposed to those through, for instance, seafood. We don't talk a whole lot about that in our paper, but there is a limited amount of data that have explored those issues. Now, the figure that you're seeing here is sort of the diagram of that marine plastics cycle, but it's worth noting that there are other environments that microplastics could be released into that also interact with human food systems. So a lot of industrial processes like polymer recycling or incineration, also tire wear, and other processes have been shown to be able to produce high concentrations of airborne plastic particles that then could settle out into, for instance, agricultural lands or other environments that interface with human food systems. So there are a number of other processes through which microplastics could get into human food and therefore be consumed. Our interest in this paper initially was to survey the literature that has itself surveyed human foods for the presence of microplastics and nanoplastics. There are dozens and dozens of studies over the last decade and a half that have basically taken sampled foods around the world for the presence of these small plastic particles. Some of the major categories that have been investigated are shown in this slide. So not surprisingly, a lot of food derived from the ocean, like seafood, fish, crustaceans, mollusks, sea salt, but also bottled water, municipal tap water, beverages, dairy products, and then some studies on things like meat and vegetables and honey and sugar. The list goes on. The major ones are shown here. One of the first things that we really set out to do was to do a really quantitative meta-analysis to find out what this literature was showing, but it became abundantly clear very early on that a high-quality meta-analysis was going to be almost impossible, mostly due to the fact that the methods that people were using to analyze these foods, analytical methods, the purification methods, varied considerably from study to study. The quality of studies varied considerably. The way that data were reported were also varied quite a bit. So it's just really hard to compare the results of one study to the results of the other to get a high-level view of what the prevalence of microplastics are in some of these foods. One of the few categories that we were able to do a meta-analysis on was the polymer type, and the results of that analysis are shown in this slide. So up and down, you see a lot of the different types of polymers that have been observed in these food categories, and the size of the circles are sort of the relative prevalence You can see there's not a whole lot of difference from food type to food type, and it's usually the usual suspects like polyethylenes, polypropylenes, nylons, polystyrenes, and so forth, but not a large amount of variation from one food group to another. This slide, I know there's the text here is really small and you're not meant to be able to read all that, but this slide is a screen capture of one of the large tables in our manuscript. So basically what we wanted to do here was to provide an overall survey of what we felt was the high-level takeaway from the analysis of each type of food that has been analyzed. So along the left-hand column are the different food groups, which I've already sort of mentioned, and then we tried to summarize in a sentence or two what we felt was a kind of a high-level qualitative conclusions of what the current data needs were for those types of food categories. So you can see that detail if you want to go check out that paper. Along the right-hand side are references. So we did try to be very comprehensive and list sort of representative primary sources of some of these studies that have been done, the ones that we felt were fairly high quality, as well as focused review articles on microplastics in these different food categories. One other thing that you'll see in this table are a list of the primary regulatory authorities for these food categories in the United States. When we were doing this analysis of the literature, one thing that we found that was consistently lacking was any focus on who was actually responsible for oversight of food safety of these different food categories. And we felt that would be really useful information because these regulatory authorities are important stakeholders in this problem. So we did list in this table the agencies agencies that are primarily responsible for regulation of these different food categories in the United States. And we also provided some references to more information. So that's all in there. As far as the state of the science goes, some key points to take home are the one that is that microplastics have been reported in a range of human foods. Pretty much every study that we looked at did report finding microplastics in various numbers and with various properties, but that those studies vary greatly in terms of experimental design, with many lacking quality controls or appropriate application of the analytical methods. This really leads to an inability to compare, particularly quantitatively, across different studies, which really makes it hard to understand exactly what types of nanoplastics and microplastics are in foods, how extensive the problem is, and what the concentrations are. The origins of microplastics detected in foods are uncertain. What I mean by that are two things. One is that if you were to do a lot of these studies that did analysis of foods for microplastics, they report some quantity of plastics and they do some sort of characterization, but it's really hard to know how many of those reported microplastics were originally in the food before the analysis was done. Labs can be dirty places. Microplastics tend to be everywhere, and so there's a high probability that a lot of the microplastics that are detected are contaminants from the lab. Over the last decade or so, researchers have become a lot more aware of this problem and have taken a lot of steps to reduce the potential for contamination. They do things like use a lot of blanks and controls, cleaner labs, and so on. But it's really hard to know how effective those procedures are, and they're often applied still inconsistently. And it's just really impossible to know if for any given microplastic, whether it was something from the lab environment or was originally in the food. It's also, even if we assume that all the microplastics that are detected in the food were there before the analysis was done, it's really hard to know how they got in the food to begin with. The analysis just tells you whether the microplastic is there and what its properties are. So if you look at something like a fish and you're analyzing a fish and you find microplastics, the question is, did the microplastics, were they taken in through this bioaccumulation process through the marine environment? Were the microplastics introduced after the fish were caught, when they were processed? Did the microplastics originate from packaging? There's really no way to really pinpoint the exact origin of those microplastics. And it's an important question because unless we know where they're coming from, it's hard to devise mitigation strategies. Currently, the scientific evidence do not demonstrate that microplastics in food pose a risk to human health. It's just really important to underscore that the mere presence of microplastics does not imply risk. This body of literature really only reports whether microplastics are there. Most of those studies do not do any sort of analysis of the potential health impact to humans, although a lot of them do use very alarmist language, which is really to be discouraged without evidence. And finally, there's very little data on nanoplastics in human foods. So these are particles, again, for the purposes of this paper, that have at least one dimension less than a micron in size. And that really comes down to limitations. So it's a great segue into the sort of what I want to talk about with the back half of my talk, which is analytical methods to detect and characterize microplastics in foods. Before I talk about the actual methods, I'd like to take a step back and talk a little bit more about microplastics. So far, I've been kind of referring to them as though they are a monolith, but in fact, microplastics are actually mixtures of really heterogeneous mixtures of things, of particles that can be categorized in a lot of different ways. And so this figure tries to capture some of the different properties of microplastics that can be measured or that they can be categorized by. Probably when most people think of microplastics, the first property that comes to mind is size, because a size indicator is in the name microplastics. And we can categorize these by size. As shown on the left-hand side, these particles can range anywhere from the smallest single-digit nanometers up to particles that we can see with the naked eye. Particles can also be categorized by their shape, so sphere, film, fragments, and so on. These shape categories are not very well defined, even though people do try to assign shape indicators to particles when they do their analyses. Color, density, the polymer type has already been discussed a little bit. Origin in this context refers to how the particles got to be the size that they are. So we usually refer to particles as either primary or secondary microplastics, primary microplastics being plastic particles that were intentionally manufactured to be that size. So these can be things like microbeads or nurdles. Secondary microplastics are those that were degraded to be the size that they are through natural processes. We can talk about the surface properties of microplastics, so molecules that are adsorbed onto the surface of these particles, or other chemicals that could be absorbed into their interiors. And finally, we can talk about age of microplastics. These plastics, are they pristine, or are they weathered? Are they oxidized particles? It's important to underscore that that it's really not understood yet which of these properties of microplastics is important to know in order to determine potential health effects. So usually what happens is that researchers, when they're doing a survey of a particular food, they'll go in and measure as many of these as they possibly can, which requires a lot of different analytical techniques. A final property that really needs to be discussed is that of concentration. So for conventional chemical analysis of foods, the concentration units that usually are used are mass-based units. So for whatever the chemical is, you would usually measure a certain mass of that chemical in a certain mass or volume of a food. You can do that with a microplastic or a nanoplastic, but more typically we find concentrations expressed in particle number-based units, so like number of particles or number of objects per volume of food. The reason is because these are objects, and so as we'll see, typically the way that they're measured is to physically count them. So it's just a natural unit to use. The problem is that it's not really clear which of these concentration units are most relevant from a health impact assessment. So if we go through and we do all of our measurements in particle-based concentrations, and it turns out that mass-based concentrations are more important than those particle-based concentrations, may not have a lot of utility, and it's very difficult to convert between these two metrics after the fact. So the real challenge for analysis of microplastics in foods is that uniquely identifying microplastics or nanoplastics requires isolating these particles, organic particles, from an organic matrix without changing their properties, and then measuring several different of their characteristics using techniques that are not often common to food analysis laboratories. If we take a 30,000-foot view of this literature of analysis of microplastics in foods, they all tend to follow a similar workflow, which is captured in this flow diagram. The typical way that you have to do it is that you take your food matrix and then you have to extract those particles from the food matrix. There's a lot of different ways you can do that. You can do an extraction, you can do some sort of filtration, or you can do a selective digestion of the food matrix and hopefully leave the particles intact. Which of those methods you use depends a lot on the food matrix. Either way, when you have an isolated sampling and hopefully representative sampling of your particles, then the next step is usually to put them under a light microscope, and the analyst physically counts the particles that are there and records their properties. So things like the size, the shape, and the color. And then you can build histograms of those particles and their properties for plotting out. The other thing that one usually does is subject those particles. Usually it's now typically interfaced with a light microscope as an FTIR or Raman measurement. Those measurements provide information on the polymer type as well as potentially the purity or state of degradation of the microplastics. So this is how you can assign them to be like polyethylene or polypropylene and so on. All those data are then aggregated and processed in some way, typically binned into categories, and then they can be plotted out and then hopefully do some sort of analysis. This workflow poses a lot of challenges. There's a lot of opportunities for environmental contamination, which are shown there in red. Already talked about some why that's a potential issue for microplastics analysis. Pre-treatment steps may alter the microplastics characteristics, and there are also well-known potential for bias in any microscope-based method. This workflow, for the most part now, only provides concentrations in a particle number basis, without consensus that this metric is the most relevant for a health impact assessment. Also, there are mass-based methods available, but they've really lagged in development behind the particle-based methods. That's been improving over the last couple of years, but there are still very few published assessments of microplastics in foods that use these mass-based detection methods. Because FTIR and Raman are so ubiquitous now in the literature, I thought it was worth to just pause on these two methods for a minute or two, because there might be a number of people in the audience who are unfamiliar with these techniques. Raman and FTIR are both vibrational techniques. They work under the principle that every molecule has a unique structure, and bonds in every molecule vibrate, and so the vibrational patterns in each molecule are unique. Infrared radiation excites those vibrations, and so because the vibrations are different, they absorb unique frequencies of light. And so an FTIR infrared spectrum provides a fingerprint for each individual chemical structure, including polymers. So the idea is that, which is captured in that data there that's shown on the slide, is that once you have your microplastic particles on for instance, a microscope slide, you can point your light source or your laser on the one of those particles, obtain an infrared spectrum, and then the software attempts to match that spectrum to a reference library to determine what the polymer type is. Additives and contaminants to plastics also have their own unique vibrational spectrum, and so in principle you can also detect what those additives and contaminants are. Raman and FTIR are both vibrational techniques. The underlying physics are different, but as a practical matter for microplastics analysis, they both kind of do the same thing. The biggest difference between Raman and FTIR is that Raman has a spectral resolution of about 1 to 2 microns if you push it, and FTIR has a spectral resolution on the order of 10 microns. So Raman is able to have a smaller, a better lateral resolution than FTIR. That lateral resolution is an important metric because it defines the smallest structure that one can reliably view with a microscope. So you basically can't see anything that has a size smaller than that lateral resolution or spectral resolution. And this is really the chief reason why we can't reliably detect nanoplastics, because they're basically too small to see with these two techniques. It's also a fundamental limit imposed by the properties of light, so there's no real easy way to modify these to be able to detect smaller particles. So although there are some methods available for nanoplastics, there still aren't really any really good widely used solutions to that problem yet. FTIR and Raman microscopy have a couple other limitations. The analysis tends to be really slow and labor intensive. You are going through and sort of detecting one particle at a time. Most microscopes can automate this process, but you're still limited into the size of the window and the number of microplastics you can detect at any one time. So most of the published analyses tend to be limited to a few dozen particles of characterization. The process of library matching is also not standardized. It's prone to a lot of errors and false positives, particularly as the particle size gets really small, because of the amount of noise that's introduced into the measurement. When you have additives and contaminants, or the particles are partially oxidized, or they're made of more complex plastics, the libraries may not contain any reference information at all. So it might be very hard to assign a compositional category to these types of particles. Or the software may just do its best and misassign it. So there's a lot of room for uncertainty in these sort of library matching, in this library matching process.
So Tim, if you conclude, we have a couple of questions for you. Otherwise,
yeah, I got like one or two slides left here, if you don't mind. So what does this mean for data needs for methods? So basically, the workflow that I showed you, there's nothing inherently wrong with it. The problem is that it's not consistently applied. The methods that are used are differently. The analytical methods that are used are different, and also the purification and isolation procedures are different. So really, what we need are consensus definitions and fit-for-purpose metrics, standards and certified reference materials. We need better standardized sampling methods. We need better fit-for-purpose standardized and validated methods for quantifying unknown microplastics and nanoplastics and their mixtures. We need further development of mass-based microplastics and nanoplastic quantification methods. And we need the use of real-world mixtures and concentrations of microplastics and nanoplastics in method development initiatives. So as far as summarizing the key points, FDA does not generally comment on specific studies, but evaluates them as part of the overall body of evidence to further our understanding of the issue and assist in our mission to protect public health. It's really important to underscore the point that FDA does not usually consider single studies. The last thing you want to do is make some sort of decision based on a single study that turns out to be incorrect. So it's really important to have a body of literature that's of multiple studies that are showing the same thing. Due to the inconsistent and often inappropriate application of methods, it's not yet possible to quantitatively assess the prevalence of microplastics in human foods or assess their properties, origins, and potential biological effects. The scientific evidence does not demonstrate that microplastics in human foods pose a risk to human health, and investment in analytical methods development and standardizing the application of those methods will result in more reliable data on the prevalence of microplastics in foods and health, and also more expedient transition of standardized analytical tools to the regulatory environment. As just a last word, FDA is continued to be interested in this area. We continue to monitor the state of the science. Our work group meets on a regular basis to discuss these issues. And recognizing the importance of this issue, FDA recently launched an outward-facing website. This was just in the last month or two, that you can see here. So if you're interested in this topic and want to know what FDA is doing, I encourage you to check that out. That's the URL, but you can easily find it through a Google search. So with that, I'll close my presentation. Thank you very much for your attention, and I'm happy to take a couple questions. I'm sorry I went a couple minutes over, but hopefully I left enough time for some questions.
Thank you, Dr. Duncan. That was very interesting. We have 3 questions in the chat, but I'm going to hold the one on safety of fish for consumers till after Dr. Coffin's presentation. So Jay Patrick wants to know, if you have to do a digestion to isolate and detect particles, what does that tell you about about their accessibility after ingestion?
I'm not really sure what the person means about accessibility. But
Well,
I
it
mean,
means you've bypassed what the human would experience while you're digesting for the analysis.
well, I mean, so in order to do any kind of these analysis, you have to isolate the particles from the food matrix, right? Because you can't you're just not going to be able to see them with a microscope if they're sitting in like tomato sauce or something. So it's almost imperative to do that. It does raise a good question, and I sort of touched on it, and that is the fact that anytime you do anything to isolate particles from the food matrix, there's the potential that you change the properties of the particles. So although you can do an analysis on pristine particles that are free from the matrix, the central question is that a fair representation of what the particles are like in the food? There's no easy way to answer that. The more aggressive the procedure is, probably the worse it's going to be as far as a fair representation of the particles. So when you do a digestion, you're going to have to use a harsh chemical to do that, to get rid of the organic matrix. And the real trick is these are also organic particles. So there's always the potential that anything you do to get rid of that food matrix is also going to partially degrade that plastic particle. So I think it's a really great question as to how are we sure that whatever measurement we're doing or whatever way we're taking to isolate those particles is giving us reliable data on what those particles actually look like in the food.
So, Tim, there are a lot of FDA-specific questions in the chat. Maybe while Scott is presenting, you could start answering some of them, because we won't have time to get to all of them, if you would. I'm going to introduce Scott Coffin now to make sure he has time for his presentation. Dr. Scott Coffin has a PhD in environmental toxicology and serves as a pharmacokinetics research scientist at the Office of Environmental Health Hazard Assessment in the California Environmental Protection Agency. Since 2014, Dr. Coffin has led research projects to characterize hazards and risks of microplastics and their associated contaminants. From 2019 to 23, he worked at the California State Water Resources Control Board, where he developed a regulatory definition of microplastics, as well as the state's monitoring plan for drinking water. Dr. Coffin, the floor is yours.
Thank you for the nice introduction and for getting us started with a nice overview of the state of the science, Dr. Duncan. So I'm going to be speaking from a sort of different perspective from a state agency, the California Office of Environmental Health Hazard Assessment. We are a small but mighty group of toxicologists here in California that evaluate the hazards of different contaminants. And I specifically have been studying microplastics for about 10 years now. So I'm going to give you a bit of an overview of what California has been doing and what we know and where the direction we're going. So starting off with another disclaimer. So I work for the Office of Environmental Health Hazard Assessment, or OEHA, and the views are that I'm going to be expressing in this presentation are from myself, and do not necessarily reflect the views or policies of OEHA or the California Environmental Protection Agency. So now that that's out of the way, I want to first bring us to where California entered the game, so to speak, in terms of microplastics as it pertains to human health. And We need to go back to 2017 to really see where this story started. This is the first time that any scientific publication had come out regarding the contamination of microplastics in drinking water. This groundbreaking study found plastic fibers in 83% of tap water samples globally and in 94% of samples in the United States. And it just took a couple months for California to react. And taking a step back and really looking at the trajectory of the public's concern on the microplastics issue, this is, I think, a very telling group of pictures here with the 1955 cover of Life magazine touting throwaway living as a way of replacing chores, this advent of disposable products. All the way up until 1997, we're seeing advertisements for plastics being an important part of your healthy diet with no sense of irony there. And then now in 2020 and this new decade, we are seeing much more concern in the public about our consumption of microplastics and plastics in general. And in 2018, just months after that 2017 study on microplastics in drinking water came out, California's legislature responded to the issue with a groundbreaking bill that would require the California State Water Resources Control Board, part of the California Environmental Protection Agency, to address the issue by first setting a regulatory definition of microplastics for the purposes of drinking water. And then by July 21st of 2021, we were required to develop and adopt a standardized analytical method for monitoring microplastics in California's drinking water supply, and then come up with a plan for 4 years of testing and analysis and report those results to consumers. We were also considered to develop a health-based guidance level, which would inform consumers about the relative risks of microplastics consumption to the state that we were able to do according to the science. And then, of course, accredit laboratories so that we can feel confident about the results we're getting of our monitoring campaign. This is the same year, California's legislature passed a similar but more ambitious and broad bill regarding microplastics in the marine environment. And this required the Ocean Protection Council and the state water boards to initiate a statewide microplastics strategy by 2022 to deal with, again, microplastics in our oceans and freshwater environments. And by 2026, we are required to develop a risk assessment framework, standardized analytical methods for monitoring in ocean water, tissue, sediment, develop or establish baseline occurrence data, and figuring out the sources and pathways of microplastics into sensitive marine environments. We're also required to recommend some source reduction strategies or mitigation strategies back to the legislature. So in considering a definition of microplastics, Dr. Duncan set this up really well in terms of it really is no consensus, as microplastics is a rather difficult thing to define because it is a spectrum of different properties, including size, shape, polymer, charge, adsorbed contaminants. There's really a lot of different ways that one could think about this universe of particles. And despite that, despite a lot of uncertainties and ambiguities in the literature, the state water boards adopted the world's first regulatory definition of microplastics for the purposes of drinking water monitoring back in 2020. And we defined this contaminant suite very broadly so that we're including lots of different particles that may turn out to we may discover later are hazardous, and we want to make sure that we're capturing them in our definition. So this includes particles from 1 nanometer all the way up to 5 millimeters. We do differentiate nanoplastics. We use an upper size limit of 100 nanometers to be synonymous with nanoparticles in the literature. And the only exclusion that we provide are for actually natural products. So products that have not been chemically modified other than by hydrolysis. So of course, the polymers that are included are all of the ones with those chasing arrows on the bottom, so-called traditional plastics. But we also include non-traditional plastics that have been excluded from other definitions like the ISO and ASTM definitions, including synthetic rubber, fibers, silicones, bio-based and biodegradable plastics, as well as cellulose acetate, which is a chemically modified form of a natural product, cellulose. So definition out of the way, we can talk a bit about what we're actually doing to address this problem. In 2021, again, we had this requirement to develop a standardized method and accredit laboratories. At the time, there were no standardized methods, so we developed our own with the help of the Southern California Coastal Water Research Project, or SWRP. They involved 26 laboratories from 7 different countries in an inter-laboratory validation study in which we developed methods for Fourier transform infrared and Raman spectroscopy. And we validated these methods using drinking water, ocean water, fish tissue, and sediment matrices. So each of these laboratories received a set of particles. There was a test matrix of particles, and we asked them to extract the particles using a standardized method, and then categorize each of these particles using microscopy. This is often done with computers, taking pictures and measurements, and then verify the chemical or the polymer identities using either FTIR, Raman, and in some cases, some of these labs use pyrolysis GCMS. We sent each of these labs blind samples with known quantities of 4 different polymer types in 4 different size fractions and 4 different shapes. We also threw in false positives, such as sand, shell fragments, cotton. And looking at the overall performance of these laboratories is a little bit disappointing in terms of the recovery percentage, which is shown on the y-axis here in log scale. You can see here that the median is about 30%. This is a very low recovery by analytical method standards, but you can also see that there's extremely high variability. And this is not the whole story. If we break this up by size fraction, we can see that most of the low recovery is associated with the 1 to 20 micrometer sizes. These are very small particles that are often very difficult to categorize and count. And we see much better recovery in larger size fractions. There's also some biases in terms of colors as well as shapes. These reflect some self-contamination from analysts and difficulties in characterizing certain types of particles. We also characterized the cost and the amount of time that it takes to run these these methods. And we determined that these are not going to be cheap analyses. These instruments are rather costly. Infrared and Raman spectrometers cost at least $100,000 and sometimes much more. And these samples can take a very long time to analyze, as many of these analysts are using manual techniques to run the samples. Automation is developing and it's getting much, much better. But at the time that we ran this study, it was taking about 10 hours to 15 hours, depending on the method that people were using per sample. Based on this understanding that these methods are not cheap and take a long time to run, we developed an idea to utilize a suite of different methods to get different information for fit-for-purpose monitoring. This is an idea that had already been developed for a similar contaminant suite, per and polyfluoroalkylated substances, or PFAS, where you used a so-called surrogate method like total fluorine, something that's rapid and easy to run, to get an idea of how much contamination you may have in your sample before going to more specific and complicated and expensive methods. Our tiered framework is still under development. We are testing out a couple of different surrogate or tier 1 methods, with our tier 2 method being something like Nile red staining, something you can get a good idea of the types the total amount of plastic in your sample without understanding what the polymer types are, or maybe the shapes, and reserving this more complicated method for smaller number of samples. We currently provide accreditation for 2 methods that are available on our website, State Water Board Microplastic 1, Revision 1 for FTIR, and Revision and Microplastics 2 for Raman. The accreditation is provided by the Environmental Laboratory Accreditation Program. Any laboratory in any country can apply. Currently, we have 2 laboratories that are accredited, the Moore Institute for Plastic Pollution Research, which is a nonprofit, as well as the McCampbell Analytical, which is a for-profit company. So look out for additional laboratories becoming accredited and coming online soon. And now I want to get into the management of the issue, what we've been doing from a ecological perspective, and talking a bit about Senate Bill 1263's implementation. So first off, to understand the hazards of microplastics, in 2020 to 2022, we convened a workshop of experts in the field to consider the available literature and provide recommendations to the state for what type of dose metrics may be relevant for effects, whether that be the mass, the particle count, the volume, the surface area, what particle characteristics influence toxicity, what the adverse effects in humans and organisms are, and if we have enough information to develop thresholds for regulatory use. In terms of the hazards, we determined that microplastics have 3 main ways of causing harm. One is the particles themselves can be toxic to cells, as well as different ways for different organisms. Pathogens can adhere to these particles and be transferred, and chemicals can transfer from the particles to organisms once ingested. In terms of chemicals, there are many that are added to plastic intentionally and non-intentionally, at least 10,000 that have been characterized in the literature, of which 2,400 are considered substances of concern based on their hazard profiles. And unfortunately, 53% of those are unregulated in the United States currently. 11% of the toxic substances lack some sort of scientific reference. This was from a 2021 study. And when it comes to the pathogens, we are seeing a large number of research come out about the ability for plastics to allow long-range transport of microorganisms, including quite dangerous pathogens such as Cryptosporidium, Giardia, and Toxoplasma. We are also seeing the ability for plastics to serve as an enriching hub for antibiotic-resistant bacteria. And this field is rapidly developing, but we don't have enough information to develop a quantitative risk assessment framework for this particular toxic mode of action. What we do have enough information to characterize quantitatively, and what we applied in this 2022 workshop, was the consideration of particle-based toxicities to both humans and ecosystems. And for ecosystems, we did a literature review and found 167 toxicity studies for characterizing harm to 117 different species. And we whittled these studies down to the ones that we considered to be reliable and relevant based on a robust set of quality criteria. Only 22 studies were left with data for 16 species, which then underwent another level of expert review. And then we did what's called a data alignment, so that we're comparing apples to apples, so to speak, between these studies. And then we did what's called species sensitivity distribution modeling to get an idea of how much these particles may be harmful towards an ecosystem as a whole. So in terms of the alignments, the idea behind this is that in environmental settings, organisms are exposed to an extremely diverse type of particles, a mash of particles. So we consider this to be polydisperse. One way of thinking about this is like a fruit basket, where you have many different types of fruit, different shapes and sizes and polymers. And in a laboratory, we can expose organisms to often one type of fruit. Sometimes laboratory studies will expose organisms to a representative mixture of microplastics, but most times they're using polystyrene spheres of 5 microns, polyethylene fragments of 20 microns, yada, yada. So we had to find a way to reliably compare between these studies. And we used an idea called toxicologically relevant metrics, or TRMs. And for ecosystems, we consider 2 relevant TRMs. which are food dilution and tissue translocation. The idea behind food dilution is very simple. Basically, plastic has no nutrient value, and when it takes up space in an organism's gut, it can prevent them from getting nutrients from other sources, especially if it accumulates in the gut and cannot be egested, such as in the case of some organisms like birds. In this case, we only care about the particles that can be ingested, and we disregard the particles that are bigger than the mouth size of the organism, and we consider the volume of the particle to be the relevant metric. For much smaller particles that can translocate into the body and be taken up into tissues and interact at the cellular level, we consider the surface area of these particles to be the relevant metric, as the surface area is what's interacting with the particles around them. So using these toxicologically relevant metrics, we are now able to compare between different studies by aligning them to different size, density, and shape distributions based on an environmental profile. I won't go into the maths behind that because it's very complicated, but in effect, what we can do is we can compare these studies and develop a species sensitivity distribution to conservatively estimate harm towards an ecosystem as a whole. Typically, regulatory agencies like the US EPA will base their assessment on the 5th percentile of species to which harm may be predicted. We did a similar sort of derivation where we're using the 5th percentile. We also used the 10th percentile of the species sensitivity distribution in the case of a high tier threshold called source control measures. This is a theoretical framework for getting at different levels of certainty and uncertainty of the particular harm. Because there is so much uncertainty in the field as a whole, we wanted to provide a range of different thresholds with conservative thresholds on one end and less or least conservative thresholds on the other end, so that managers may have an understanding of when there really is a problem and when there could be a problem. So these 4 different thresholds, from investigative monitoring to source control measures, are shown here for the food dilution and tissue translocation toxicologically relevant metrics measured in particles per liter, aligned to the 1 to 5,000 micron size range, so what's colloquially known as microplastics and many different definitions. So one could compare those particle concentrations to that size range in the environment and quantitatively assess their risk. However, distributions of microplastics differ between different environments, depending on the sources of the microplastics, as well as other environmental attributes. And an organization may want to consider different species, for example, in their particular hazard assessment. Maybe they're not concerned about some species like algae, or they're more concerned about certain species of commercial or societal relevance, cultural relevance. So we developed an interactive application, web-based. This is an open source and free tool called the Toxicity of Microplastics Explorer, or TOMEX. What's being demonstrated here is how to derive a species sensitivity distribution very quickly just by clicking through this app. It does all of the maths and simulations for the user in real time. We are currently updating the literature the database in the TOMEX app. The first version, we had 162 publications for aquatic organisms. We've added quite a number. We're up to 287 now, and that brings our total data set more than double. We've got nearly 13,000 toxicity data points in this Explorer. And so this is going to be published soon, the updated version of TOMEX. Currently, we are working on the making this open access to everyone. And I want to show you briefly how one would actually apply these hazard thresholds into the environment. This was a study that I published in 2022, comparing the hazard profiles, or the quantitative hazard thresholds that we developed with environmental monitoring data collected in the San Francisco Bay using what's called a manta trawl net, shown here. This is the overview of the samples and how they compare to those quantitative thresholds. You can see here everything in green is below all of our thresholds, which would indicate that there is very limited risk occurring in those environments. with the yellow showing investigative monitoring has been exceeded, that threshold. And so you can see that almost all of the samples within San Francisco Bay indicate that there is likely some risk already occurring, with one sample even showing an exceedance of the highest least conservative threshold for considering source control measures. Based on our understanding of fate and transport, the flow of buoyant particles in different environments and in San Francisco Bay, this risk modeling really makes a lot of sense, as we're seeing a high accumulation of particles in the mouth of the bay based on the tidal influence that brings the particles back into the bay and then back out on a daily basis. We also considered the uncertainty of this assessment using Monte Carlo methods, considering the uncertainty and the underlying parameters that we did to make the alignments. And we can see here that we have relatively high uncertainty for all of these different thresholds, exceedances, ranging between 25% to 100% of samples exceeding our most conservative threshold. Based on this uncertainty and this assessment, the State Water Resources Control Board made a recommendation to the United States EPA that several of these water bodies in San Francisco Bay be put on the Category 3 list of the 305B, which is part of the Clean Water Act. This would indicate that there is not enough information to support, there's not enough information to determine if the beneficial use of this water body has been threatened, but there is information that indicates that it may be threatened. So we're in sort of an uncertainty range here, where we would like to do additional monitoring to really characterize this risk. In terms of the health-based guidance level that we applied for human health or derived for human health, we were working with far fewer number of studies. Just 29 ingestion-based in vivo mammalian microplastics toxicity studies were available at the time, and we whittled these down to 12 studies that we deemed fit for purpose, which then underwent expert review. And just showing an overview here of the endpoints that were filtered through that we considered to be reliable in these studies. The vast majority of the available information back in 2022 indicated potential hazards to the reproductive system, particularly in males, with 2 studies indicating relevant impacts to female reproductive endpoint of anti-Mullerian hormone concentration. These, all of these studies were done in rodents. Almost all of them were done in rats. And the overall consensus from this assessment really is that there may be some harm happening here, but it's very difficult to relate what we see in these rodent studies to humans for a number of reasons. When it comes to the dose response assessment of these different studies, there were some relatively high uncertainties for some of these concentrations. But what we did find overall is that regardless of the particle size used, the relative magnitude of the point of departure, or the relevant level that may cause harm was in a fairly tight mass range. So it ranged from about 0.05 to 10 milligrams per kilogram day. So this is relatively small considering the very wide number of or sizes of particles that were used. So we did this point of departure development using EPA's benchmark dose modeling software. In terms of the particle trait that we consider to be most relevant for human health in this particular instance, we look towards the nanoparticle literature, which has determined that the surface area of particles are a much better predictor of harm than the mass of the particles. None of these studies were measuring the surface area of the particles. Almost all of them were just dosing based on the mass. However, we can estimate the surface area of these particles based on the known geometries of the particles used, as well as the density of the polymers. Another thing that we learned from this assessment is that microplastics are more likely to translocate into tissues when they are smaller sizes, with about 10 microns being the nominal cutoff. Above this size, we don't really see accumulation in organs or in tissues. And when it comes to relating these hazard studies to what we're being exposed to, there's a lot of uncertainties here. But what we do know is that we are being exposed to microplastics in many different ways. We are seeing it in different tissues, including in lungs, blood, placenta, breast milk, testes. There's probably many more as these studies are being published quite often. In order to quantitatively assess risk, one would compare the exposure to the hazard. And if there's an overlap, then we may be concerned for that particular population. When it comes to the exposure characterization for microplastics, there's extremely wide uncertainties and variability. A lot of the uncertainty is due to the differing types of methods that were used. Self-contamination is very common in a lot of these methods, so there's only a small number of methods that are, or studies that have been actually considered reliable. But if you look at the exposure range from this probabilistic assessment, you can see here that the median for the total on the right, it hovers around 10 to the negative 4 milligrams per capita per day, which is equivalent to about a grain of salt per week. The 99th percentile of this assessment is below a credit card per week. So many people cite that credit card per week of microplastics. We consider this to be extremely unlikely scenario. What's shown here is in purple is the benchmark dose range. So from this reliable hazard endpoints, there is some overlap with the interquartile range for exposure. However, we still don't have enough information to determine if this is actually indicative of risk to the population. In terms of exposure routes, when it comes to food packaging, we know that this is a likely exposure route for humans, as polymers degrade when you use them. When you unscrew the cap of a water bottle, microplastics shed on the order of 14 to 2400 from one study. Opening a snack bag releases 14,000 to 75,000 microplastic particles. There's a lot of uncertainties when it comes to our exposure to from plastic packaging, and there may also be some exposure from the food itself. So the particles getting into food during the processing, during the growing. There's really a lot of research that needs to be done in this field. But one thing we also know is a very relevant exposure route is if you are heating your food in plastic, particularly in a microwave, you are dramatically increasing the amount of microplastics that get into that food product. This was a study in 2023 that found a very small, relatively small number of microplastics get into your food from plastic packaging when it's cold, when the food is cold. But when you put it in the microwave, you increase the amount getting into the food to on the order of billions of particles. So don't microwave your food in plastic. When it comes to indoor exposure, we consider inhalation to be the most dominant route. We have a lot of information for the amount of microplastics and dust that's going on in our homes. Between 2 and 13% of household air or household dust is made of microplastic, and it is 15 times more concentrated in indoor air than it is in outdoor air. This is almost exclusively fibers that come from carpets, rugs, any upholstery that you have in your house, even your clothing, are constantly shedding microfibers. So taking a step back, getting back to this 2022 assessment, the expert work group determined that we simply do not have enough information to derive regulatory levels for microplastics in drinking water today. This is due to an effects database being inadequate. Many of these studies were not doing a good job characterizing the particles that they exposed organisms to, and they only tested a limited set of polymers, shapes, and sizes. We have an uncertainty with regards to the effect mechanisms. This is necessary for extrapolating to diverse particle types using those toxicologically relevant metrics. Ideally, we'd have an understanding of the adverse outcome pathways for these different effects. And of course, we have incomplete exposure data, which I mentioned. We have very limited data on what's actually in our food, and we currently have no harmonized way of comparing between studies, as people are not using standardized methods. At least they weren't in 2022. We are seeing people using the State Water Board standardized methods for monitoring and drinking water and other matrices in the literature now. So that's going to greatly enhance our ability to reliably compare studies in a meta-analysis going forward. We published a set of recommendations for how to move this field forward and some additional research that's needed to assess human hazards. So you can read about that in the open access journal, Microplastics and Nanoplastics. And we are updating Tomex 2, not just for aquatic organisms, but also for human health. This will be coming soon, next year. We added 22 studies for human health, nearly doubling the database. When it comes to regulatory responses, what California is doing is we currently have a brand new mandate. This was just adopted a few weeks ago, Senate Bill 1147, which requires my agency, OEHA, to study the health effects of microplastics in drinking and bottled water and provide a biennial status update on our findings. Following our report, the State Water Resources Control Board may request my agency to develop what's called a public health goal for microplastics in drinking water, which then can be used to develop a regulatory standard or maximum contaminant level. In terms of testing, we currently have a plan for 4 years of testing and analysis in California's drinking water, and we'll mostly be looking at microplastics in surface waters as opposed to groundwaters, as surface waters are much more susceptible to contamination from particles in general, and microplastics specifically, than groundwater sources, based on the circulation of particles in the environment through wind and rain, wastewater, different sources. And groundwater has a natural filter barrier. So sediment does a really good job at preventing particles from getting through. However, this does depend on the type of sediment. If you have an extremely large grain size like sand, it's going to be much more likely to get particles through than a small grain size like clay. If there is a discontinuity, such as a fissure, this can be in a karst environment, so like in a cave or something. This could allow particles to get through those discontinuity bottlenecks. And we are seeing literature come out on this for microplastics specifically. A 2023 study demonstrated that when it rains in a karst environment, you get a lot of microplastics pushed through, which can then go into the groundwater. And interestingly, a 2015 study found microplastics in in groundwater, and they attributed it to a septic system in Illinois, and they were able to determine this based on an analysis of the chloride levels. This is a really interesting study, and I think deserves a little bit more info. This particular field deserves a lot more research. When it comes to California, we don't have a whole lot of karst environment, so we're not very concerned about microplastics in our groundwater. But the rest of the United States has a lot more karst, especially the East Coast and central of the United States, mostly carbonate. That's where a lot of the cave systems are. This is where we may be more concerned about microplastics in groundwater. So we published our 4-year monitoring plan on our website back in 2022 through the form of a policy handbook. This approach is considering the limitations in our analytical method and leveraging the methods that we currently are reliable, are deemed reliable. So microplastics, when they get into a surface water, and are then taken into a surface water treatment plant, drinking water treatment plant, most of them are going to be filtered out. Flocculation and sedimentation does a very good job at getting rid of particles that are as small as about 1 micron or so. More advanced filter technologies like microfiltration, reverse osmosis are going to get rid of much smaller particles. But if you're just using flocculation and sedimentation, you're likely not removing nanoplastics. It's just really difficult to monitor them, especially with our current methods, which are limited to particles down to about 20 microns or so if you're using Raman, 50 microns if you're using FTIR. So based on this limitation where we can't really detect the particles that are actually of human relevance and that are actually getting through the treatment processes, we are going to be monitoring in the source waters for the first 2 years. We know that microplastics size distributions are highly conserved across different matrices like freshwater. And so we can reliably extrapolate the number of smaller particles in a system from the larger particles that we can quantify, much like we could interpolate what's below the surface of an iceberg if we understand the shape of that iceberg and we can measure what's visible. So we have this 4-year plan for monitoring. Right now, we're in what's called the pilot phase. It's going to be wrapping up in 2025, doing a bit of research to make sure that when we go out and monitor in California, we are using the best available techniques and collecting the data in the best way possible. 2025, approximately summertime, we're going to be requiring the first set of systems monitor for 2 years and report the data. So it's going to be in source waters only. And it's just going to be limited to about 28 systems in California, some of the largest water systems in the state. And then in 2027, we'll reassess and develop our phase 2 monitoring. We have a data portal that will be open to the public. It's already live. A bit more on that later. I want to make sure that I have enough time for Q&A. So
Well, I think we need to wrap it up.
okay. Yeah, I'll just go to the end here. So just wrapping it up. So in terms of going forward, we have a data portal that is open to the public. It's open source, and this allows for harmonization of the data reported to the state, but also this is a portal that is open to anyone. Anyone can upload data for any place in the world, making it a harmonization portal for microplastics globally. It's called One for All. And just ending on a note of inspiration, the microplastics community is built on sharing freely open source methods, tools, databases, code, resources. There are hundreds of these things out there, and they're often scattered in websites, supplemental information of different articles. And so what I've done is made a crowdsourced method for collecting all these different gems from the rough and putting them all in one place. This was a passion project, volunteer effort that I put together with a couple of close friends and colleagues to develop the plastiverse.org. Our mission is to remove barriers on plastic research and share information widely to the public. So go check out plastiverse.org. And if you want to get involved and be up to speed on what California is doing for monitoring microplastics, I invite you all to attend our quarterly meetings of the Microplastics Monitoring Subcommittee. Our next meeting is on November 12th from 11 to 1 p.m. And I can paste the information in the chat if you'd like to attend these meetings. And I believe that's all the time I have. I look forward to hearing from everyone, your responses and feedback.
Thank you. That was really informative from both of you. Tim's been doing a really great job of answering all the questions in the chat, but one just came up. What are the largest contributors to nano plastics and microplastics in America, and what can we do? What's our priorities of what we could do?
I can take that one. So in terms of nanoplastics in particular, it's really going to depend on what scenario you're talking about. So human exposure to nanoplastics, we think most of that is coming from the fibers that are in our homes and on in our clothes, as well as the degradation of food product packaging, such as like microwaving things. And when it comes to what we can do about that, installing an air filter in your home is a very cost-effective means of reducing your personal exposure, as well as avoiding the use of particularly heating plastic packaging. Your personal environmental or plastic footprint is dominated by the consumption of single-use plastic packaging, as well as washing machines. So when you put your synthetic clothing in the washing machine, the particles come off of the clothing and are sent into the wastewater treatment plant, which oftentimes are then sequestered into biosolid and land applied. So the best thing that you can do to reduce your personal plastic footprint is to consume less synthetic clothing, install a washing machine filter to collect the fibers, and consume less plastic packaging in general.
Thank you both. This was great. I think I need to turn it over to Elizabeth. I think you're frozen, Elizabeth. Well, she was going to tell about the next seminar, which she'll have to do by advertising. So thank you on behalf of Phi Tau Sigma, everyone who joined today. And I hope you gained as much as I did out of the wonderful presentations.